Alright, we have this function and we want to be able to graph it. So to do this, we need to know how to find certain key points. Well, probably the first thing I would do is figure out what the domain would be. Well, there's nothing up here showing that it's a closed domain. In other words, I didn't give you intervals. So I just look at my function and see, can I pretty much plug in anything into this function? So it'd just be all real numbers, right? Because I don't have a square root that I'm worried about taking the negative of a square root. I don't have a fraction. I'm not worried about dividing by 0. I don't have something like a logarithm where you can't take the logarithm of a negative number. So everything looks good. Alright, so then the next question is I want to find the open interval where the function is increasing and then also where it's decreasing. So to do this, I know where a function is increasing, the derivative would be positive. Where it's decreasing, the derivative would be negative. So I guess I need to take the derivative, right? So if I take the derivative, I get negative 6x squared plus 12x. And from here, I set this equal to 0. And then I want to solve for x because I want to create my interval around my next part that's going to ask me is my extreme values, my critical points. So I probably would factor out a negative 6x, so that leaves me a positive x minus 2. I set both of these factors equal to 0, so negative 6x equals 0, and then x minus 2 equals 0. Of course, if I divide both sides by negative 6, I get my first critical point, x equals 0, and then this side over here, I'm just going to add 2 to both sides, and I get x equals 2. So these are going to be my critical points that I'm going to set up my interval. So let's kind of do that over here. So I have 0 and 2. And remember, here I want to pick values that are to the left, like negative 1, in between, like 1, and then 3. And I'm not restricted with any values, right, because we just said the domain's all real numbers. Well, once again, remember, you're plugging these into the derivative, because when you plug them into the derivative, if you get a positive value, you know it's increasing. You get a negative value, you know it's decreasing, and all that good stuff. So if I plug in negative 1 into this piece, right? So negative 6 times negative 1 squared plus 12 times negative 1. As I've said before in class, I don't really care what that number is. All I care is it's positive or negative. And it's going to end up being negative. Then I'm going to plug in 1. So negative 6 times 1 squared plus 12 times 1. You can certainly see the positive is dominating the 12, so that's positive. And then I plug in 3. Negative 6 times 3 squared plus 12 times 3. And you can definitely see on the left side the negative is going to dominate, so I get that. So really, this tells me already what this graph looks like. And this is important that you understand what this means. That says on this interval, the graph is decreasing. When it hits that critical point, it goes flat, because that's where the derivative is 0. Then on the interval from 0 to 2, it's increasing. When it hits 2, it goes flat, and then it decreases. So this tells me a lot of stuff already, right? It tells me where it's concave up, where it's concave down. It tells me where I have min, max. And it also tells me I'm probably going to have a an inflection point somewhere in between 0 and 2. And I'm only going to have one inflection point. Because remember, an inflection point is where it's changing concavity from concave up to concave down. And it's only doing that in one place. So even though we're going to go through all these steps, this step right here gives me a lot of information. All right, so keeping kind of with the design, then D asked me for extreme values. Well, going back up here, I can certainly see I'm going to have a local min and a local max. So my min is going to be at x equals 0, right? And then my max is going to be at x equals 2. Well, I want to evaluate those. I want to find the y values, so I go back and I plug them into my original function. So negative 2, 0 cubed plus 6 times 0 squared minus 3, and I get negative 3. F of 2, negative 2 times 2 cubed plus 6 times 2 squared minus 3, and I get 5. So I know then at 0, negative 3, I have a local min, and at 2, 5, I have a local max. Again, this is in a restricted domain, so I'm not going to have globals. This function, in fact, you could probably go back up here and put arrows. It's going to go a lot higher, and it's going to go a lot lower. All right, where are we now? So then we get into wanting to look at the intervals of concavity. The intervals of concavity have to do with concavity. Make sure I can spell it without talking. This has to do with my second derivative. So my second derivative, and I already kind of see that it's concave up to that point, and then it turns concave down. So to that point is what I need to find, which is my inflection point. How do you find the inflection point? You take the second derivative. So that would be what, negative 12x plus 12. I'm going back and looking up there. I took my second derivative. From here, I would solve this. I would set this equal to 0 and solve for x. So I can move the 12 to the other side, subtract it on both sides. I get negative 12 equals negative 12x. And then, of course, I can divide both. Hello, don't do that. And then, of course, I can divide both sides by this negative 12. And I get x equals 1, which is my inflection point. Well, to find the concavity intervals, I do the same thing I did up here with my number line, but I just do it with my inflection point. I mean, we pretty much already know the answer, hopefully. If you understand the show, right, what's going on, I already know that it's concave up from minus infinity to my inflection point 1, and I already know it's concave down from 1 to infinity. But let's just prove that. So again, we pick values to the left. 0 always looks good. A value to the right. And we plug that into the second derivative. So I'm plugging that into the second derivative. So here was my second derivative. If I plug in 0, I get negative 12 times 0 plus 12. So that's positive. It's happy. It's concave up. I plug in 2, so I get negative 12 times 2 plus 12. That's negative. It's sad. It's concave down. We kind of already saw that up above. But I have this business going on that it's concave up. It turns, and then it becomes concave down. One last final question would be, what's the inflection point? So I know it's at x equals 1, but I need to go back and plug it into my original function to get my y value. So -2, 1 cubed, plus 6 times 1 squared minus 3. I get 1, so 1, 1 would be my inflection point. So from here, I can pretty much graph everything based off of all this information. So I have and I've pretty much been graphing all the way, but all I would want to do from here is just label my points. My min is 0, -3. My inflection point was 1, 1. My max is 2, 5. And then of course it might be nice to find intercepts, and I leave that up to you because that's algebra, right? But let me remind you, so an x-intercept is when y equals 0, and a y-intercept is when x equals 0, and we actually already know this because that's at our min. Okay, so that was our 0, -3, so I can label that as an intercept as well.